Welcome to our talk about the present and future of interprocedural optimization in LLVM. My name is Johannes, and I give this talk together with Stefanos, Kuter, Shinji, Luofan, and Hideto. Let's start with the present.
Hi, I'm Shinji. I'm this year's Google Summer Course student. I'm going to talk about the present situation of IPO in LLVM. So let's begin with classifying the existing IPO passes into some categories according to their purpose or their logic. The first is inliner family. Inliner represents call size with the body of call function. There are, for example, always inliner, and inline advisor. The second is passes that propagate information between caller and callee. There, for example, attributor, IPS-CCP, info function array pass. The third is passes that modify linkage or optimize globals. For example, global DCE, global opt, and global split. And others, for example, merge function, open MP opt, hot call splitting. If you are interested in more detail of these passes, please check out the IPO tutorial for that. Next, let's see the performance of IPO passes with a result of an experiment using SQRise3 benchmark from test suite. SQRise3.c is quite a big file. Consists of more than 80,000 lines of C code. We compiled this with O3 option and debug pass option. We can get information about executed passes with this debug pass option. The result is this. Immutable, loop, and function passes are intra-procedural passes. And CDSCC and module passes are interprocedural passes. So, this shows that more than 90% of executed passes are intra-procedural. Okay. Next, I'm going to show how much inlining affects the performance of compiling. Let's compare with two cases. One is with inlining, and the other is without inlining. When we disable inlining, the walk time decreases by 54%, and the time needed for pass execution decreases by 61%, and the time for instruction section pass decreases by 65%, and the size of emitted machine code size decreases by 47%. So this shows that 50%, more than 50% of time and space are spent as a consequence of inlining. One point we should be aware of is inlining itself doesn't take much time. Middle end passes or back end passes executed after inlining does take much time, because of the code duplication caused by inlining. That's the point.
Howdy, I'm Stefanos Baziotis, and we're going to talk briefly about inlining. In case any inlining expert is interested, I'm planning on making a bigger talk on inlining. So if you are, please contact me. And there's also going to be a part on inlining in this year's tutorial that we're giving, called a deep dive into procedural optimization. So the biggest benefit of inlining is code specialization. It's one of the biggest enabled transformations. So you can see here that caller 1 and caller 2 call foo with a different second argument. There were actually no action compile time. But if we actually go to analyze foo as it is, we know nothing about the second argument. But now if we inline the call, we actually know we can remove this if in both places altogether. Now this solves also drawbacks, because imagine that foo has more stuff there. And you actually inline this call twice. And what's going to happen is this more stuff is going to appear in two places now. Again, so then, even worse, you can see that if we had a caller 3 that calls foo with exactly the same code, and we inline that as well, you see that now in color 2 and color 3, there's exactly the same code. Okay, so in all these places, you actually try to run optimizations. You're gonna run on fuse code multiple times, and it's the same code. Basically, you're gonna repeat work. Another drawback of inlining, which, well, to understand it, I truly suggest that you watch the tutorial because we're explaining better how inlining in LLVM works. So in LLVM, inlining is the bottom-up inlining. So you start from sinks and you go toward the sources in the call graph. And so one example that this bottom-up inlining might fill is you might have this call chain where basically A calls B, B calls C. And so the idea is that these functions are likely actually complex functions. And what happens is that at the top we have constant arguments. So these constant arguments could, make constant propagation and constant folding work, and they could simplify a lot these functions, right? This B, C, and D. But actually, because inlining runs very early on, that might not happen. So then the inliner might start from the bottom, and inliner again knows nothing about these constant arguments. So the inliner might try to inline bottom into D, D into C, but at some point it's going to stop because, again, these functions are complex. At some point the inliner is going to say maybe these functions, heuristics say these functions are quite big right now. And so the inliner stops there and it doesn't move to the top, at which point it would know that this constant argument simplified a lot of these functions, and so it could take very different inlining decisions. So the final thing to see is that basically bottom-up inlining works in SSEs because otherwise you have cycles. And so if you inside an SSE, there's no actually clear way. There's no clear order to go. So you can either go top-down or bottom-up. There's no clear order. So I think the LLVM inliner just walks the SSE a couple of times to try to understand what is the best way to traverse that. As a side note, GC's inliner doesn't impose an order. It basically has some kind of a queue where basically inlining candidates are allocated based on some weights. Okay, so because again imposing an order actually limits you in some way. There's no clear good order. And as far as I understand it, bottom-up inlining is actually better than top-down inlining because you start from the sinks, and sinks are like self-contained things that you don't have to know a lot about them, a lot outside of them, actually, I should say. So, right, so that was for me for this talk. Thank you very much.
If we talk about inlining, we should also talk about alternatives. And instead of just talking about interprocedural optimizations as we have them in LLVM, which are certainly alternatives to inlining, let's go a step further. Let's look at inlining across translation units. This is one of the main benefits you get through LTO or thin LTO. Even like for thin LTO, inlining and the inlining heuristic are actually a main driver that determines what functions are copied from one translation unit into another. Alternative to that, you can do interprocedural optimizations through function attributes. Basically what we do with the function attribute deduction and with the attributor, but not only inside of one translation unit, but across translation unit. This scheme was presented last year at the LLVM Developers Conference under the name HTO. Let's take a look at how those two compare. What you see here is the speedup of HTO on the left and the speedup of thin LTO on the bottom. And the highlighted area shows you that a lot of the speedups that we achieve on the LLVM test suite with thin LTO are actually matched by HTO. That is, a lot of times it's not about the inlining and the specialization, but it's really just about summarizing the effect of a function, such that at the call sites we can use that effect. However, there are certainly outliers where thin LTO performs far better than HTO. Those can be cases where specialization for the one call site is important. We identified at least two of those to be indirect function calls, which you can specialize to be direct function calls. Similarly, it might just be that other caller-callee optimization trigger after you inline. However, there's also the possibility that we're just lacking the right attributes, such that while we already increased the number of attributes over the last year and a half, Once we increase it further and have more fine-grained attributes, as we'll discuss later in this talk, we get better optimization opportunities just through attributes and function summaries without actually needing to inline.
Hello, my name is Kuter. Now I'm going to talk about the design space of IPO. So we can actually think of it as a triangle, where in which side there is the interprocedural optimizations, things like argument promotion, IPSCCP, classical things that propagate information between callee and caller. Right? In the other side, we have inlining, which essentially eliminates the call edge by copying code from the callee to the caller. Right? But that can result in code bloat, which can have bad effects in terms of memory locality and compile time, simply because we have more code. Right? In the other side, we have function specialization, which is essentially copying the contents of the function for a specific subset of call sites. In the most basic way, this could be taking an externally linked function and making it internal by copying its contents. That allows us to essentially propagate information from the call sites to the function itself, right? That can not only it can optimize the contents of the function, that can also give us more information in terms of the return value and the way that the function interacts with the arguments. So in the function specialization, we can not only for taking an external function, but we can also take a function that has a lot of call sites, and we can actually copy the function for similar call sites, right? That way we would have different versions of the function that are specifically optimized for a specific sets of call sites. Currently in an LLVM, we are more oriented towards inlining. We have some really good interprocedural optimizations, we have good inlining, and actually our current options that are available to us are not, doesn't give us a great coverage of the design space possible, right? But I think in the future we can have a greater balance between inlining, interprocedural optimizations, and function specialization. And in the future, I believe we would have better coverage of the potentials of the IPO, right? So inlining, we have inlining, and for better interprocedural optimizations and function specialization, I believe that the attributor can do the heavy lifting.
Before we go to the future, let's look at yet another problem of the current pass pipeline. The ordering is rigid. So we have these passes, some of which are interprocedural, mostly in the beginning. Then we have a lot of function passes which are intraprocedural. Then we have the inliner, and then we go to the next strongly connected component in the call graph. However, those passes cannot communicate with each other. And if you have a function that is recursive, has loops, or is otherwise complicated and would require multiple of those transformations to analyze and apply to the code at the same time, you will not get the optimizations you are looking for. This code can be transformed to a simple return 0. And while you can run the O3 pipeline as it is, as often as you won't get that. The attributor, however, performs various things at the same time through its interprocedural fixpoint analysis. And we will later show how the attributor, how the different components of the attributor, the abstract attributes, communicate with each other to perform the optimization on this program. So let's take a look at the future.
Hi, I'm Luofan, and I'm one of the GSOC students working on the attributor this year. And I want to show how the attribute can make a difference to the current situation. We hope the attribute can improve the IPO infrastructure and make it more powerful and give more optimization options in the future. So, the attribute is an interprocedural fixed-point iteration framework with lots of built-in features. There are 2 videos about the attribute on the dev meeting last year, and you can check them out if you want to know more about the detailed implementation and ideas behind it. For this part, we will focus on the features and potential of the attributor. The attribute can do a lot of things such as inferring IR attributes, simplifying and deducing variables, and rewriting function signatures, making it cover a lot of existing IPO passes such as function attribute passes, IPSCCP, and argument promotion. One advantage of the attribute is how the runs of abstract attributes are scheduled. So as shown before, the code on the right is not well optimized by LLVM to return 0 because no matter how many times the O3 pipeline is run. The problem is that the function attribute path cannot mark this function as no capture, as it is not sure about the unknown function, and the IPSCCP path cannot make sure the check and inc function does not change the value of x and y. But the attribute will solve the problem in another way. The attribute will construct a dependency graph during the iterations, and here is part of the graph generated by the example above. The idea is that every abstract attribute can query the state of other abstract attributes, and if any abstract attributes changes, all abstract attributes that queried this before will be scheduled to update later, until we reach a fixed point where all abstract attributes remain unchanged. By doing this, we keep all the information up to date, and any abstract attribute can always get the latest and detailed information at other positions of the code. In this example, what the attribute will do is that it will create an abstract attribute at the return position of test, that is x plus y, and it will try to deduce the value of it. So in the test function, we are given the attribute is given that x and y is initially 0, and based on that information, the attribute can safely conclude that the potentially escape use of x in the check and inc function is dead, and so no uses of x writes x. Then it will conclude that x is 0. So that's y, and the return value is then simplified to 0. The attribute can also do function internalization or specialization. That is, we make copies of functions based on this function's linkage or contact. The example shows that we have function 4, which has link1's ODR linkage. So IP optimizations cannot be applied to it because it may be replaced at link time, and the information derived from it may not be useful. But since the ODR indicates that this function follows the one definition rule, we can make a copied version of it and change the uses of the original function to the copied one. Here we copy the function 4 as 4.internal and make the 3 callers called the internalized one. By doing so, we enable the interprocedural optimization of the non-exact functions. And we can also do fine-grained function specializations for different call sites. Here, based on the bool argument C of 4, we create 2 versions of the function. One assuming the function, the argument is false, and the other true. And we can replay the call with different copied versions based on the values of the bool argument. Such internalization is like inlining, but we can control the granularity, minimizing code duplication, and use the information derived from other parts of code to improve such internalization. The attribute also supports fine-grained time traces. Here are the time trace results with and without the attributor. Those are the features that we want to highlight in the attribute. Thanks.
Hi, I'm Hideto. Here I'd like to talk about how to get there
I mean how to improve the current situation and barriers to enable Attributor by default. First, we have a problem about attribute annotation for library functions. Today, many built-in functions are annotated with some attributes, but it's far from perfect. There are a lot of missing attributes. We have to fix this problem because in IPO, we summarize the information about the entire program, and if any built-in function isn't properly annotated, the whole result can easily get very bad. So we need more annotations. Recently, opt-out attribute annotation is introduced, so this will improve the library annotation. And in this example, heap to stack conversion is prohibited by ill-annotated library function. In this case, the optimization doesn't success because memcopy doesn't have no free function attribute. But clearly, memcopy doesn't free any memory, so when no free is added to memcopy, we got better result. Another way to introduce better optimization is to annotate more information to the program. Here, I'm gonna show you some ideas. On the front-end level, we can introduce generic LLVM IR attribute, or some new attribute like access. We can put LLVM IR attribute on C and C++ program by using generic LLVM attribute. And GCC has access attributes which annotate more precise specification about memory access. Maybe we can use this in LLVM. On LLVM IR level, we can introduce more precise attribute for memory effect. Something like related to error now or more precise memory locations. Currently, there are attributes related to memory locations like argument memory only or inaccessible memory only, but sometimes a function may access either argument or inaccessible memory. However, we cannot represent this information on current VM, so maybe we need to create some more flexible attribute. Another idea is a potential value attribute. This attribute annotates values which the annotated value may become at the runtime. In fact, Attributor has this attribute internally. If we create this attribute officially, we can easily connect to Attributor and cause more optimizations. From now, let me explain the current situation of Attributor to enable by default. I think Attributor has a lot of tests, so the test coverage is reasonable. But Attributor is not tested on CI regularly because Attributor is not disabled. Because Attributor is disabled by default. So we maybe want to have a build bot which tests Attributor. Another concern is memory overhead. We have worked on reducing memory overhead, and it's improved, but we have to improve more. We are now working on dropping states which are not useful anymore in the middle of the deduction, or creating abstract attribute only when it's really necessary. Similarly, there is a compile time regression. It is improved, but we have to improve as well. We are now working on the scheduling of updates of the state. This kind of fixed point iterations, the scheduling of the update is really important. And we recently disabled some costly deduction by default. The deduction is powerful, but it was too costly. So if you want to use it, you can use it with some option.
We want to get the best performance for the amount of compile time that we spend, right? For that, we could do selective investment, in which we essentially focus on the hot code and only look at the cold code only when it is needed to make deductions about the hot code. To give an example, let's take a look. The sync function here is marked as cold, right? And which essentially, is, as it lives in this block, makes the rest of the block cold as well, right? And when we want to make deductions about the bus function, we want to use the arguments that are coming to it, right? We look at essentially the values of p, right? If you think of the way that it would be in the IR, there would be a phi naught here, right? So if we look at different values of the p, so one of them is of course the turn value of the bar function. Even though we don't really want to spend time on the bar function, we only analyze the return value of the bar function to make deductions about it. Alright, so that way we essentially selectively invest our time to make deductions that we want, that we think that are important.
To conclude, let's take a quick recap. We've seen that the majority of passes that we run is intraprocedural. We're heavily reliant on that still. We've also seen that inlining has positive effects on performance, but it has negative effects on code size and compile time. Literally, if you copy the code, it is not surprising that you afterwards have more code, in that it takes longer to actually work with more code. Alternatives to inlining are interprocedural optimization, in which we summarize all the effects for all the call sites, or function specialization, where we summarize the effects for some of the call sites and specialize a function for those. Together with the attributor framework, where information can be shared based from different transformations and analyses that are in flight at the same time, we really think that the design space that we have here is much bigger than what we explored so far, in that going with the attributor towards interprocedural optimization and function specialization will open up way more options to trade in execution time and compile time and code size. Here are the references we linked during the talk. I hope you have questions and join us in the Q&A. Thank you.
We will review the tags.
Hey, Stefan, I think you introduced us.
Oh, I missed that we're live. Sorry. Thanks for watching our talk, and thanks for joining our Q&A session. I guess we'll start with the question with the most votes. So here we go. First question: any heuristics to choose between inlining, specialization, or IPO based on performance, size, or compile time requirements?
Yeah, that's a good one, obviously. Heuristics are tough. Right now, we are, in the attributor side of things, we're pretty much aggressive, or like you have like on or off, aggressive, non-aggressive switches. We started to work on a heuristic to do specialization during the summer, but it is not mature enough to be integrated. Inlining obviously has a heuristic. IPO, as we have it in the pipeline, otherwise is just run on everything. So we're not actually like selecting much there. So it's really the only place where you really can choose between all three of them, or at least to some degree, would be the attributor framework that has more control in deciding if it leaves something for the inliner, if it specializes something, or if it applies IPO, potentially even hinting to the inliner at some point if the inliner should leave things alone or not, or inline them for sure, in case we could reasonably argue that inlining would not be beneficial or that inlining would be really beneficial. We could start to communicate there as well.
Anyone else has something to add?
Just a small note. Basically, I think that since IPO apart from inlining, has not been developed much, as far as I know, to most compilers. Really, I don't think there are good heuristics because there's not enough experience even. So.
Okay, we're moving on. So the next question is asking whether or not there will be new attributes in the future.
Wants to take that one? Hideto, you want to comment on that?
Mm-hmm. Yeah. So, yeah, I think there are more precise memory locations or potential values will be good ones because, yeah, it will introduce a lot of optimizations and easily introduce them. Yeah.
We also have a couple of attributes already in the pipeline for people that might have followed LLVM dev and also the fabricator emails. There's at least 2 attributes that are pretty much ready that are going to come out. Must progress to ensure a forward progress guarantee for functions and or loops. And the other one is max object size, which you can kind of think of as almost the opposite to dereferenceable. One of those two gives you kind of a lower bound on your remaining object size. The other one gives you an upper bound on your object size, which together can be used to improve aliasing results. And while the RFC is going to come out end of the week for the latter one, the max object size, you can find that one in our tutorial last year about the attributor. So we actually introduced it last year. We just kind of forgot about it. And we have some results in an attributor attribute to an abstract attribute to deduce it. And we have some results with and without the attributor to show that it improves aliasing results, that it improves things like loop invariant code motion and other transformations. So those 2 are pretty much done and in the pipeline, and then others are going to be tested.
Thanks. So moving on. So the question is, are there any suggestions on the best practices to write interprocedural optimizations with as little compile time overhead as possible? What data structures have high memory footprint?
Kuter, are you gonna go over that? I think
So
you have a good answer.
okay, so I actually had been working on trying to improve the memory footprint of the attributor. So I think for the first part of the question, which is to write saying interprocedural optimizations. So I would say, even though I could be a bit biased, I think attributor framework would be a good choice to integrate your interprocedural optimizations. There had been some other passes that had been trying to use OpenMP, for example, trying to use the attributor for some of its deductions. It was using attributor to integrate its own deductions there. So attributor as a framework, I think, would be a good choice. So the second part of the question is that data structures. So rather than data structures, so actually in terms of data structures, rather than for the taking dependencies, we have seen that integrating the dependencies dependency system to the attributes themselves, rather than tracking them in a map, it had improved our memory footprint and some performance. Other part of it is trying to not have everything in memory at the same time. So maybe by trying to do some garbage collection, looking at the functions in certain orders, that it helps us delete some of the stuff that is not needed. So we are currently working on that. That's the answer that I would give to that. So anybody wants to add anything to that?
I think it was good. Avoid maps of maps and avoid maps that are really big. And right now we managed the first part, and the second part we're working on by kind of clearing part of our state that we hold, as Kuter said, while we're iterating still. So the part that we don't need anymore. Because if you look at the whole module, these maps become big quite fast, and that is really a problem. Let's go to the next question. We don't have that much time left.
Okay, so we have a little bit more than a minute. So I see some people asking about HTO. So can anyone give like a short overview?
Yeah, so the HTO question was already answered in the chat. We had the link to the poster. Last year's LLVM Dev had a poster and a talk about HTO, which is called header time optimization. Take a look, YouTube, last year's talk about that. It's actually pretty cool, and we advanced it further, so take a look at that.
Do you want to add anything?
No.
So what about recursion and inlining?
How do we have 30 seconds? Well, in the 30-second answer, you could the transformation, again, is not difficult. It's the heuristic. And as far as I know, LLVM doesn't handle anything else than tail recursion. If you want to handle anything else, you would basically use heuristics for loop unrolling. That's, as far as I know, what GCC does and what actually makes sense if you think about that.
Great. We're almost out of time. So we're going to have a tutorial afterwards about IPO. Please go and check there. We'll have a Q&A afterward again, and otherwise ping us in the community board.
Thank you.